Welcome to AI Unraveled, the daily briefing that dissects the business of intelligence. Today we are tackling the silent budget killer in enterprise AI, the GPU scheduling nightmare. Here's the reality. You just spent $10 million on NVIDIA Hone Hundreds, but your utilization metrics are telling a different story. Your chips are sitting idle while your data science teams are stuck in queues. Why? Because default Kubernetes orchestration wasn't built for the complexities of AI workloads. In this episode, the GPU scheduling nightmare, we are ripping up the old infrastructure playbook. We're exploring how the world's largest enterprises are moving beyond basic orchestration to reclaim millions in wasted compute and securely scale multi-tenant innovation. It's time to stop burning capital on idle silicon. But before we stop marketing to the masses, start briefing the C-suite. You've seen the power of AI Unraveled, zero noise, high signal intelligence for the world's most critical AI builders. Now, leverage our proven methodology to own the conversation in your industry. We create tailored proprietary podcasts designed exclusively to brief your executives and your most valuable clients. Stop wasting marketing spend on generic content. Start delivering must-listen strategic intelligence directly to the C-suite. Ready to define your domain? Secure your strategic podcast consultation now. Link in show notes. Now let's optimize your infrastructure.
We talk constantly about this massive corporate land grab for AI infrastructure, the sheer capital being poured into building these new AI factories. We see all the headlines about GPU scarcity, the race for chips. But what if I told you that for the average large enterprise, the majority of that multi-million-dollar investment is, well, it's currently sitting idle. There's a silent systemic tax being levied on enterprise AI, and it's all because of bad software architecture.
It's really the dirty secret of the AI world. We're talking about resource underutilization on the most expensive hardware assets out there, cutting-edge GPUs. And when we look at the internal data from, global organizations, the numbers are pretty sobering.
How sobering.
Over 3/4 of companies report that even during their peak load, GPU utilization is below 70%.
Below 70. Let's ground that in a number that really hits the bottom line. If you bought just one single top-of-the-line NVIDIA H100 GPU, and that's a piece of hardware that costs upwards of $40,000,
Right.
and it's sitting idle just a quarter of the time, that's a $10,000 loss in potential value per GPU per year. For companies with hundreds or thousands of these, that waste just explodes into an 8-figure financial drain.
And it isn't due to a lack of work or a lack of talent. The root cause is really technical debt. It's an architectural mismatch. The default way companies orchestrate their compute using Kubernetes, or KS, was built for short-lived, stateless microservices. It is just fundamentally mismatched for the long-running, stateful, and resource-hungry nature of modern AI jobs.
So our mission today is to deliver the technical blueprint that leading enterprises are using right now to solve this efficiency disaster. It's a two-part solution. It has to address the CFO's mandate for utilization and, just as critically, the CSO's mandate for security. Let's start by dissecting that core flaw that causes the utilization nightmare.
Okay, so the foundational problem that engineers face is what they call the integer GPU fallacy.
Integer GPU.
Yeah. Default Kubernetes, it just sees a GPU as an indivisible unit. It's like an opaque black box device. A data scientist literally has to request nvidia.com/GPU1. You ask for a whole number, or you get nothing.
That sounds almost absurd when you think about how variable AI workloads actually are. Walk us through a typical use case where that rigidity creates waste.
Sure. Think about a data scientist in the development phase. They're running a Jupyter notebook, maybe doing some rapid model fine-tuning, or just pre-processing data. That job might only need, say, 2 to 4 gigabytes of memory, maybe 10% of the GPU's total compute capacity.
But because the scheduler insists on allocating the whole thing, that tiny developer task effectively locks the entire $40,000 asset.
That's it. The remaining 80 to 90% of the GPU just sits there, allocated, reserved, and completely unproductive.
Wow.
And this forces platform teams to massively over-provision hardware just to accommodate those short-term, low-intensity tasks. It leads to enormous capital expenditures that aren't actually solving the underlying efficiency problem.
And that single waste mechanism is then compounded by 4 specific failures of the default K8's scheduler. It fundamentally treats the pod as the unit of work, right? When for AI, the job is really what matters. The first failure seems obvious, but it's often overlooked. the failure of sharing.
It just lacks native sophisticated mechanisms for either vGPUs, that's virtualized partitioning, or even simple oversubscription using time slicing. This inability to just slice up resources and share them among multiple users is, the single biggest driver of those sub 70% utilization rates.
Okay, so that's number one. The second one leads to this kind of infrastructure paralysis, the failure of gang scheduling.
Right.
Distributed AI training, especially for large models, it's not a single server task. It's a team sport. It needs a gang of pods to launch at the same time across different machines.
But K8 schedules pods one by one. So imagine you're trying to book 4 seats together on a flight, but the airline only confirms 3 of them right away. The job, which needs all 4 to start together, is now stuck. And what happens to the 3 GPUs that were successfully allocated?
They're held hostage, reserved, allocated, but sitting completely idle, blocking other work from even starting. That sounds like a deadlock.
It creates deadlocks that can cripple a busy cluster. Then you have the critical performance bottleneck, the failure of topology awareness. The scheduler knows a GPU is available, but it has no idea about the physical architecture within the server. It doesn't know about high-speed interconnects like NVLink.
Wait, can you define NVLink for us?
Absolutely. Think of NVLink as a dedicated, private highway between GPUs inside a single server. It's NVIDIA's proprietary tech, and it can move data exponentially faster than the general-purpose Ethernet network that connects different servers.
So for distributed training, you want all your GPUs talking over that private highway.
You have to. But if the scheduler lacks that topology awareness, what's the consequence? It causes the scheduler to just blindly scatter GPUs across nodes.
Oh, so not even in the same physical box.
Exactly. Sometimes they're not even in the same server rack. So when the pods try to exchange the massive volumes of data needed for training, they're forced onto the much slower Ethernet. And the research we've looked at is really clear on this. It absolutely kills performance. It creates a network bottleneck that drastically increases training times, wasting both time and money.
And finally, there's the failure of fair share queuing, which just introduces operational chaos. You've got high-priority, customer-facing inference services running alongside, say, low-priority R&D experiments. The lack of priorities and quotas becomes a huge governance problem.
It's the line-cutting problem. A developer running a low-stakes experiment can suddenly just seize the entire cluster, blocking a high-priority revenue-generating service from meeting its SLOs, its service-level objectives. You lose governance, predictability, and ultimately you lose customer trust. The core lesson here is that Kubernetes is not by default an AI resource manager.
That paints a really grim picture of inefficiency. But now let's pivot to the second, and equally serious, conflict security. Because the CFO demands high utilization, which means sharing a cluster, but the CISO, they demand robust security, which has always meant physical isolation.
And that is the critical dilemma in building an AI factory. The first dangerous assumption we have to get rid of is that Kubernetes namespaces are some kind of security boundary. They are not. A namespace is just a logical grouping tool. It provides very weak isolation. Every tenant in a standard cluster shares the same control plane and, crucially, the same underlying node operating system kernels.
So that weak isolation creates 2 clear risks. The first one is the noisy neighbor.
That's the quality of service risk. One tenant's job, say a huge data pre-processing task, can saturate the shared memory bus, or I/O, and that throttles the performance of every other job on that node, making every application run slowly, unpredictably. But the CISO cares way more about the second threat, the malicious neighbor.
That sounds like the existential risk.
It is. If a compromised container exploits a kernel vulnerability, and they do exist, it can gain node-level access. At that point, the game is over. The attacker can move laterally to access each other's data, steal proprietary models worth millions, or even poison-sensitive training data.
And this risk is magnified by the way modern AI environments are structured, right? You have separate clusters for dev, for training, for production inference.
Exactly. This distributed structure creates all these new east-west traffic attack paths. That's internal communication between services. And traditional north-south security, like a firewall focused on threats from the internet, is completely blind to it.
Meaning an attacker could compromise a, let's say, less secure development container, use that as a foothold to move sideways through the network, and then what? Exfiltrate terabytes of training data from the production system.
Or worse, steal the company's crown jewels, the trained model weights themselves. This forces the dilemma. The CFO demands one big, efficient shared cluster. The CSO demands physically isolated, secure clusters. The CSO solution guarantees waste. So we have to find technology that gives us the efficiency of sharing plus the security of isolation.
And this is where we get to the dual solution stack that resolves this conflict. Let's start with Solution A, Advanced Scheduling. This is the software layer that acts as the intelligent AI traffic cop to maximize utilization.
The shift here is fundamental. These advanced systems reestablish the job, not the pod, as the primary thing they manage.
Okay, let's get specific. For, lightweight governance and fairness, a lot of companies start with a tool like QE. How does QE solve that line cutting problem?
QE is a pretty clever K8's native job queuing system. When a job is submitted, it goes immediately into a suspended state. QE then acts as an admission controller. It evaluates that job against these hierarchical queues and resource quotas that are specific to that team or business unit. And only when the resources and the quota guarantees are met does QE admit the job and release it to the standard scheduler. It elegantly solves the fair share problem.
Okay, but for the really high-performance stuff, those complex distributed training jobs, you probably need more firepower than just a queuing system. That's where tools like Volcano or Apache YuniKorn come in. They're purpose-built for AI and high-performance computing.
Correct. These are comprehensive schedulers, and they provide true mandatory game scheduling. It's all or nothing. This completely eliminates that partial deadlock problem and those hostage GPUs we talked about.
And crucially, gang scheduling enables these really advanced cluster optimization features, like backfilling.
Backfilling is a massive ROI driver. The scheduler can see a huge, say, 100 GPU job waiting at the top of the queue, but it knows those resources won't be free for another 30 minutes. Instead of letting the cluster sit idle, it intelligently runs smaller, shorter jobs from further down the queue during that wait. It maximizes resource use without delaying the big job.
So we have Q for lightweight fairness, Volcano for more comprehensive HPC features. Where does a tool like Apache YuniKorn fit in for a CTO building their platform?
YuniKorn is typically chosen by the largest enterprises. Think Uber, which we can discuss in a bit. It's designed as a universal hybrid scheduler. It supports both K8s and legacy systems like Apache Yarn. So if you're managing a massive hybrid data ecosystem, YuniKorn gives you a single pane of glass for all of it. The decision matrix is basically Q for simple fairness, Volcano for K8s, native HPC, and YuniKorn for that big federated enterprise-wide resource management.
That solves the utilization and efficiency problems. Now for Solution B, hardware partitioning, which is what satisfies the CSO's demand for physical isolation. When people talk about GPU sharing, the term is really ambiguous. We need to contrast the two main approaches.
We absolutely have to. We have to distinguish between time slicing and MIG. So time slicing is software-based. It's soft isolation. The driver just rapidly switches between workloads, giving each one the whole GPU for a fraction of a second. It's great for oversubscription and utilization. You can squeeze a lot of dev notebooks onto one GPU.
Okay, but what's the security catch with that software approach?
It provides no hardware partitioning. All the jobs are sharing the same physical GPU memory, the same cache, the same compute engine. This makes it super vulnerable to that noisy neighbor problem. You get unpredictable performance, and it is entirely unsuitable for production multi-tenancy, where data security and guaranteed QoS are non-negotiable.
Which brings us to the CSO's gold standard, NVIDIA Multi-Instance GPU, or MIG.
Yes. MIG is a physical hardware-level partitioning feature. It's built into modern GPUs, the A100, H100, and their successors. It physically partitions a single physical GPU into up to 7 smaller, truly isolated GPU instances.
That physical distinction is the game changer, because each MIG instance acts like it's a completely independent GPU.
Exactly. Each slice gets its own dedicated compute cores, its own slice of GPU memory, its own dedicated L2 cache. This physical partitioning provides true hardware-backed security, guaranteed fault isolation, and guaranteed quality of service. One tenant's job cannot interfere with another's performance or memory.
This finally resolves that CFO-CSO conflict. Platform teams can now securely and efficiently pack multiple tenants onto a single, very expensive GPU. You get both maximum utilization and hardware-level security.
And for the developer, the whole process is seamless. The NVIDIA GPU operator abstracts away all the complexity. It just advertises these MIG instances like nvidia.com/1G.10GBB as unique schedulable resources. They can request a secure slice just as easily as they would request an entire GPU.
Let's get to the payoff here, the ROI. Because all this technical sophistication only matters if it translates into massive financial returns. Take the case study where a company's utilization was shockingly low.
Yes, this is a multinational computer vision company. They reported baseline GPU utilization at just 28%. They were staring down an imminent $1 million+ hardware purchase just to meet demand from their R&D teams.
But instead of buying more hardware, they invested in an advanced scheduling and resource management platform. What happened?
The results were immediate and just. Massive. Utilization skyrocketed to over 73% across their existing fleet. They saw a 2x increase in the volume of experiments they could run, and they cut average training times by over 75% because they eliminated those scattering and deadlock problems.
So the core financial lesson here is that the immediate efficiency gains completely boosted that $1 million+ hardware spend.
That is the new financial model. Approved platform OpEx to save hardware CapEx. You are trading a small operational cost on software for a massive capital saving on hardware. The CFO sees an immediate, measurable return.
Now, let's look at the blueprint for a truly mature organization. Uber is the classic example here. They didn't just install Apache YuniKorn, they built a whole platform on top of it.
That's the strategic lesson right there. The real product is the platform engineering abstraction layer. Uber created a system based on hierarchical resource pools with elastic sharing. They realized simple quotas are just too rigid.
Walk us through that elastic sharing. How does that work?
So each team or pool is guaranteed a minimum number of GPUs. But if they aren't using their full allocation, the system allows other high-demand pools to borrow those unused resources. This keeps utilization high. However, and this is key, if the owning team needs its guaranteed resources back, the system's fairness algorithm ensures the borrowing jobs are preempted gracefully and returned to the queue. It's policy translated directly into automation.
That sounds like the ideal state for any massive enterprise. You maintain fairness and governance, but you also ensure that no expensive GPU sits idle, even for a moment.
Exactly. And this requires funding the platform engineering team to build that crucial abstraction layer. The layer that translates business rules like borrowing limits, priorities, budgets, directly into the scheduler's logic. That is the true competitive advantage.
And this isn't just a physical data center problem, right? The sources show the financial drain is just as bad in the cloud.
Absolutely. The waste is often harder to spot in the cloud because the billing is so complex, but the underlying problem is identical. One client running transformer models on Google Cloud's GKE realized their GPU waste was just astronomical. By implementing real-time monitoring and automation focused on efficient scheduling, they cut their GPU costs by 35%. That translated directly into six-figure annual savings without changing a single line of code in their AI model. Wow. The solution is software.
So, to summarize the comprehensive solution stack for you, our listener, we've identified the fundamental limitations of the default K8 scheduler, those 4 major failures. We've highlighted that difficult dual mandate of utilization and security, and we've mapped out the synergistic solution. Advanced, job-aware schedulers like QE, Volcano, or YuniKorn combined with hardware-backed partitioning using NVIDIA MIG.
And the executive takeaways for you are clear. If you're a CFO, you must immediately shift your primary infrastructure KPI. Stop tracking CapEx. Start tracking utilization rate and cost per job. Measure the work being done, not the capacity you bought.
And if you are the CISO, you have to mandate hardware isolation as the gas line for production AI. Prohibit that weak namespace-based sharing for sensitive data, and mandate the use of NVIDIA MIG to get that secure hardware-backed boundary.
Finally, let's leave you with this provocative thought to consider. The market narrative constantly screams about GPU scarcity. It's telling you to buy more chips, buy more chips. But the real internal competitive gap is efficiency.
In this new AI-driven economy, the future will belong not to the companies that own the most GPUs, but to those that use them most intelligently. Intelligent orchestration is the critical competitive advantage that allows you to run the most experiments, train the most models, and serve the most users faster on the hardware you already own. Now you have the blueprint to stop paying that silent tax and turn your AI cluster into an efficient, secure AI factory.
And that wraps up our deep dive into the infrastructure layer. If you take one thing away from today, let it be this. Buying the chips is the easy part. The true competitive advantage in 2025 isn't just hardware access, it's orchestration. If you aren't actively managing your GPU scheduling with granular precision, you aren't just losing efficiency, you are leaking security and burning runway. Don't let your Kubernetes clusters become a bottleneck for your best models. Audit your scheduling, secure your multi-tenancy, and turn that utilization metric into a KPI that actually drives revenue. For a deeper breakdown of the tools and strategies we discussed today, check the show notes. And don't forget to subscribe to our free daily strategic briefings on Apple Podcasts. Link in show notes. If you are ready to lead the conversation in your sector, click the link in the description to book your strategic podcast consultation with me. This podcast is researched, produced, and hosted by Etienne Newman, senior software engineer and passionate soccer dad reporting from Canada. Until tomorrow, keep your utilization high and your latency low. This is AI Unraveled.